Comets don't point at the sun. That's just not how things work out there. The solar wind blasts gas away from the nucleus. Sunlight pushes dust particles outward too. Every comet's tail, every one we've ever studied, trails behind like hair whipped back in a gale. It's practically a law of the universe. Tails always point away from the sun. Always. Except, apparently, no one told 3I Atlas. Right now, somewhere between Earth and Mars, this interstellar visitor is pulling off something that shouldn't even be possible. It's got a feature astronomers are calling an antitail, a long, narrow beam of material that stretches not away from the sun but straight toward it. 500,000 kilometers of organized matter, pointing directly at the thing that should be pushing it the other way. And as of December 19th, 2025, when it came closest to Earth, that thing was still there. Still holding together. Still ignoring everything we thought we knew about comets. Scientists across the U.S., Harvard, NASA's Jet Propulsion Lab, you name it, have had their eyes on this object since it first showed up in July. Hubble's watched it. Ground-based telescopes all over the world have snapped images. Instruments on spacecraft already in the solar system have checked it out too. And every new bit of data just makes things weirder. We don't really know what we're seeing. Not fully. Not yet. This is 3I Atlas's story. It's only the third confirmed interstellar object ever spotted cruising through our solar system. A true outsider, carrying physics we haven't figured out. Over the next hour, we'll break down everything we know, everything we still don't, and why this is one of the most important astronomical discoveries of the decade. Because when something from another star system rolls in and immediately starts breaking the rules, you pay attention. You have to. The timeline matters here. On July 1st, 2025, the Atlas Telescope network in Chile picked up a faint smudge moving across the star field. Early calculations said it was on a hyperbolic path, so not from around here, just passing through. The official name came quick, 3I Atlas, third interstellar object. That I marks it as interstellar, putting it in the same league as Oumuamua and 2I/Borisov, the only other confirmed visitors from beyond our solar system. By late July, the heavy hitters in the telescope world were locked onto this thing. Hubble snapped its first high-res shot on July 21st, 2025, when 3I Atlas was still 277 million miles from Earth, about 3 times farther than Earth is from the Sun. That image should have shown the usual, a bright nucleus, a fuzzy coma of gas and dust, maybe a few jets shooting out where the surface was venting. Instead, Hubble turned up something no one was prepared for. Around the nucleus, a smooth, symmetric glow, and jetting out from that sphere pointing right at the sun, a narrow structure that would soon be called the antitail. At first, people were skeptical. Antitails aren't totally unheard of in comet science. They've shown up before, most famously with Comet Kohoutek back in 1973. But those were just tricks of perspective. Earth lined up just right with the comet's orbit, so dust lagging behind looked like it was pointing toward the sun. It wasn't real, just a passing illusion. A few days, and the effect vanished as Earth moved along. But 3I Atlas isn't following that script. The antitail showed up in that first Hubble image in July. And it was still there when Hubble checked back on November 30th, 2025, months later, after the comet had looped around the sun and started heading back out. Earth had shifted way out of its original position. The whole viewing angle was different. And yet, somehow, the antitail was still there. Same direction, same tight structure, still doing something we just can't explain. This isn't some trick of perspective. We're looking at a real physical structure, a jet, a stream of particles, or maybe something we haven't even named yet, stretching out from the comet toward the sun. It's huge. The distance makes the moon's orbit look like a rounding error. And once you realize this isn't just an optical illusion, that it's something actually there, you start to see why scientists began asking tougher questions. NASA called a press conference right after perihelion, when 3I Atlas made its closest pass by the sun on October 30th, 2025. The official line was cautious, almost rehearsed. 3I Atlas is definitely a comet with qualities that can be naturally explained by its different birth environment. In other words, Yeah, it's weird, but there's nothing supernatural here. Comets from other star systems are born under different conditions, so they have different chemistry and behave in their own way. That's normal. Nothing alarming. Nothing that breaks the laws of physics. But since that press conference, as more images have rolled in amateurs, pros, everyone snapping shot after shot of this stubborn anti-tail, the official story feels less and less satisfying. Sure, interstellar comets probably have strange compositions. But just being made of weird stuff doesn't explain why there's a structure pointing straight at the sun. Composition doesn't defy radiation pressure. It doesn't make dust ignore the solar wind. There's something else happening, something messier, something that doesn't quite fit the models we have. So, what does an antitail even mean in regular comet physics? When a comet swings in toward the sun, sunlight heats its surface and the ices, water, carbon dioxide, carbon monoxide, and other frozen stuff, start to sublimate. They go straight from solid to gas, skipping the liquid phase. This gas jets out, dragging dust with it and forming the coma, that fuzzy cloud around the comet's core. As the comet gets closer to the sun, sunlight pushes on the dust, literally photons shoving particles away. At the same time, the solar wind, a fast stream of charged particles blasting out from the sun, ionizes the gas and pushes it straight back, forming the bright, glowing ion tail. These tails are always changing. The dust tail, made of tiny particles that bounce sunlight, curves a bit because the dust isn't all the same size. The ion tail, glowing blue, shoots straight away from the sun, lined up with the direction of the solar wind. Both tails always point away from the sun. Always. That's just how comet physics works. It's textbook. It's what astronomers have seen for centuries. So, when you spot a tail or a structure that points toward the sun, your first thought is that it must be a visual illusion, a trick of the angle, some dust along the orbital plane looking like a spike because of how we're lined up. That's basically the Kohoutek explanation, the one Z Sekanina laid out in 1974. He showed that if big dust particles get kicked out early in the comet's trip, they lag behind the nucleus. When Earth crosses the plane of that dust, it can look like there's a sunward spike, a fake antitail. It made sense. It fit the data. That became the standard model. But here, where things break down, Sekanina's model only works if you've got the geometry just right. Earth has to be lined up with the comet's orbital plane. The comet needs to have dumped enough big particles early on. Most important, it's temporary, just a few days, maybe a couple weeks, as Earth moves through that dust plane. The antitail should pop up, hang around for a bit, and then disappear. This isn't some trick of perspective. We're looking at a real physical feature, a jet, a stream of particles, or maybe something we don't even have a proper word for yet, stretching out from the comet, reaching toward the sun. It's so massive that the moon's orbit around Earth seems tiny next to it. And that moment when people realized it wasn't just an optical illusion, but something actually out there, that's when the questions started getting serious. After the comet's closest approach to the sun on October 30, 2025, NASA gave a press conference. Their message was cautious, almost rehearsed. 3I Atlas is definitely a comet with qualities that can be naturally explained by its different birth environment. The subtext was loud and clear. Yes, it's strange, but it's not unexplainable. Comets from distant star systems grow up in different conditions, so they're made of different stuff. They act weird. That's normal. Nothing to panic about. Nothing that breaks physics. But as the weeks rolled on and more data poured in, the story started to wobble. Amateur and professional astronomers kept snapping pictures. That antitail just stuck around, frame after frame. Suddenly, the official explanation didn't feel like enough. Sure, interstellar comets are expected to be oddballs, but being made of weird stuff doesn't explain a structure that points straight at the sun. Composition doesn't stop sunlight from pushing dust away. It doesn't make particles ignore the solar wind. There's something else happening here, something our current models can't quite reach. So what does it actually mean to have an antitail in terms of standard comet science? When a comet swings in close to the sun, its surface heats up. The ice, Mostly water, but also carbon dioxide, carbon monoxide, and other frozen chemicals, sublimates. That means it jumps straight from solid to gas, skipping the liquid stage. This gas jets out, dragging dust with it and forming the coma, that hazy glow around the comet's core. As the comet gets closer to the sunlight itself, photons with real momentum, pushes the dust away from the sun, while the solar wind, a raging stream of charged particles, blasts the ionized gas straight out into space. That's how you get the classic tails, a curving, sunlit dust tail and a straight, glowing ion tail, both pointing away from the sun. Always. That's Comet Physics 101. It's been seen for centuries. It's just how light and matter work together. So when you spot something aiming toward the sun, your gut says it's a trick of the eye. Maybe a spike of dust lying in the comet's orbital plane, showing up as a line when we look at it edge-on. That's the classic explanation. Back in 1974, Z. Sekinen nailed this in his paper on Comet Kohutek's anti-tail. He worked out that big dust grains thrown off early would lag behind the comet thanks to orbital mechanics. When Earth passed through the plane of that dust, those particles would line up and seem to point back at the sun. It made sense. It fit the data. That's the go-to model for anti-tails. But 3I Atlas hasn't played by those rules. This thing has hung around for months, from July right through December. It stayed put through perihelion when the comet was nearest the sun and should have been at its wildest, spitting out gas and dust and making a mess of tidy structures. Even as it's moving away and calming down, the anti-tail hasn't budged. It hasn't faded away. It hasn't twisted or shifted like a trick of perspective would as Earth's viewpoint changes. It's just there, persistent, stubborn, real. Amateur astronomers have played a huge role in tracking all this. Tirasak Thalwang, over in Thailand, used a pretty modest 26-centimeter telescope and snapped a photo on December 13, 2025. His shot clearly shows the anti-tail stretching straight toward the sun. Tony Scarmato, another independent observer, grabbed images on December 9th and 15th that show the same weird feature. Michael Yeager in Austria probably took the most jaw-dropping image so far, back on November 28th. Not only does his picture show the anti-tail, but there's also what looks like a second, parallel streak, another line of material right next to the main one. These aren't fancy space telescopes with billion-dollar price tags. These are skilled folks using good, but totally accessible gear, confirming what the pros are seeing. And when you put these images through enhancement techniques, especially the Larsen-Sekinen gradient filter, which brings out faint details, the anti-tail just pops. It becomes this razor-sharp line, perfectly focused, not spreading out like you'd expect from random dust. It looks structured, almost engineered. Honestly, it doesn't look like anything we've seen before in a natural comet. Avi Loeb from Harvard has been one of the loudest voices calling out how bizarre this is. Loeb's no stranger to controversy. He's the guy who suggested Oumuamua, the first interstellar visitor we spotted in 2017, might actually be an artificial object, maybe even a light sail from an alien civilization. That idea got a lot of flack. Most astronomers pushed back, saying Oumuamua's odd behavior could be chalked up to natural processes like hydrogen ice outgassing or other weird but not alien stuff. The general agreement was, probably natural but still super weird. With 3I Atlas, Loeb's being more careful, but you can tell he's fascinated. He's written up papers and blog posts digging into this anti-tail, and while his conclusions are cautious, they're also sharp. This structure doesn't fit neatly into standard comet models. It needs an explanation, and the ones that work force us to stretch what we know about comets themselves. In a paper with Eric Kido, Loeb offers up a model. The anti-tail is made mostly of ice grains, not just dust. These ice grains get blasted off the sunlit side of the comet's nucleus. Since they're ice, they sublimate as they travel, but not instantly. They last long enough to create a visible structure, and because they shoot off toward the sun, you get this anti-tail. It's a smart model. It sticks to standard physics, sublimation rates, radiation pressure, particle size, all that. It explains what we see without needing anything crazy or alien. But it does depend on some pretty specific conditions. The comet's spin axis has to be almost exactly lined up with the sun. The ice grains need to be just the right size, big enough to survive but still small enough to see. The sublimation has to be uneven, stronger in the direction facing the sun, which raises another question. Why would the sunlit side spit out particles harder in one direction than another? Even if you check all those boxes, there's still a problem. The model doesn't quite explain why the antitail is so sharply focused. Why doesn't it fan out? Natural outgassing creates jets, sure, but those usually spread. The pressure isn't uniform, so any tiny change in direction gets magnified as the particles travel. With 3I Atlas, the antitail is more like a laser beam than a jet. Its opening angle is tiny, somewhere around 6 to 8 degrees. That's crazy tight for something powered by thermal processes and random particle ejection. Loeb's pointed out that 3I Atlas's rotation axis seems to line up within about 8 degrees of the sun's direction. Astronomers figured this out from brightness changes seen in July and August 2025, which hint at how the nucleus is spinning. If the axis really is aimed almost straight at the sun, that's not normal. Most comets spin all over the place, with axes pointing every which way. Getting an axis lined up like this either takes a wild stroke of luck or something that nudged it into place. Maybe a close brush with a massive object in its past, or some internal shift as gases vented and shifted the comet's balance. And this is where things get really weird. If the comet's rotation axis points at the sun, the spot where the antitail jet shoots out, the actual place on the nucleus where the material comes from, has to be on the night side before perihelion, and then, after perihelion, it's on the opposite night side. Just picture that. If the comet spins with its north pole aimed at the sun, the south pole stays in the dark. If a jet erupts near the south pole, it points almost straight at the sun, giving us that antitail. But after perihelion, as the comet loops around and its angle changes, the night side flips. Now the North Pole is in shadow. For the antitail to keep going, you'd need a new jet firing from the North Pole, pointing sunward from the other side. So now you're talking about two active regions, more or less opposite each other, both able to launch these focused jets, both somehow only turning on when they're in shadow and switching off in sunlight. That's not wild for comets. Sometimes they have vents or cracks that act as escape hatches for gas and dust. But having two perfectly opposite that behave this way, like Loeb says, that's anomaly number 15 on this comet's growing list of oddities. And that list isn't just trivia. One weird thing, fine. Two, maybe just chance. But when you start piling them up, 14, 15 more, you can't just shrug it off. Something's up. So let's walk through a few of the other strange things scientists have found about 3I Atlas. First, the orbit. This comet moves on a retrograde path, meaning it goes the opposite way from the planets. That's not super rare for comets from the Oort cloud. What's weird is how closely its orbit lines up with the ecliptic, the flat plane where Earth and the other planets travel. It's aligned within about 5 degrees. Statistically, most interstellar objects should come in at all sorts of random angles. To find one that lines up this precisely, that's just odd. Not impossible, but definitely weird. Second, its close brushes with Mars and Jupiter. 3I Atlas zipped by Mars at about 29 million kilometers, and it'll get within 54 million kilometers of Jupiter's orbit soon. Not close enough to hit anything, but weirdly precise for an object supposedly just drifting through. It almost feels like someone charted a path to check out the inner planets, then swing by Jupiter for a gravity assist or maybe just a better look. Third, that rotation rate and axis alignment. Not just that it points at the sun, but that it does so even when it's far out, where the sun's gravity shouldn't matter much. Something lined up that axis long before the comet got close to us. Fourth, the coma, the cloud of gas and dust around the nucleus. It's strangely symmetric. Most comets have uneven comas because jets only fire from certain spots, so you get bright patches and dim ones. But 3I Atlas, its coma seen in Hubble and ground-based images, looks like a perfect sphere. about 40,000 kilometers across, just this glowing ball of scattered light. That kind of symmetry is rare. Either the whole surface is outgassing evenly, which doesn't usually happen, or maybe the coma, made of something that reflects light differently than normal comet dust. Fifth, the size problem. Early guesses for how big the nucleus was ranged from 440 meters to over 5 kilometers wide, a massive gap. More recent work, including NASA's analysis using Hubble, points to the smaller end, maybe a few hundred meters up to 2 kilometers. But there's still a lot of uncertainty. And that matters. The size tells you how much gas and dust the comet should produce, which changes how you judge if what we're seeing is normal or way more active than expected. Sixth, carbon dioxide takes center stage here. Spectra, especially those from the James Webb Space Telescope, show that the coma around 3I Atlas is packed with carbon dioxide, way more than you see in typical comets from our solar system. Normally, water ice steals the show. As it turns to vapor, you get that signature water and hydroxyl signal. But with 3I Atlas, carbon dioxide leads. Water's there, but it's playing backup. That mix hints at a comet that formed somewhere really cold, farther from its star than the usual water-rich comets. So odds are, this thing comes from the distant outskirts of another star system, maybe their equivalent of our Oort cloud. That's a big deal. It gives us a peek into conditions out there, but it also throws a wrench in our usual models since we don't have many examples like this. Seventh, there's barely any non-gravitational acceleration. Usually when comets vent gas, those little jets act like thrusters, nudging the nucleus off its predicted path. Astronomers track that and use it to figure out how much gas is coming off and from where. But with 3I Atlas, its orbit sits right where gravity says it should. This could mean the nucleus is heavier than it looks, so the same gas jets just don't move it much. Or maybe the outgassing is balanced, with jets firing in opposite directions and canceling each other out. Eighth, let's talk about how well this thing is holding together. Comets are delicate, just loose piles of ice and rock barely held together. Get them close to the sun and they can split apart without much warning. We've seen comets break up in spectacular fashion, but 3I Atlas, it's still in one piece. No big chunks flying off, no obvious breakups. That could mean its nucleus is tougher than most, or maybe it's just not taking as much heat stress as we expected. Maybe the outgassing is more controlled, or the makeup of the comet gives it extra strength. Ninth, methanol. Recent observations have spotted a lot of it coming off 3I Atlas, about 40 kilograms per second. Methanol is interesting because it's an organic molecule, and finding it in comets always gets astrobiologists excited. It's a basic building block for more complex chemistry. The amount here is pretty high, and since methanol boils off at lower temperatures, it means the comet can stay active even far from the sun. So now we've got another piece to the composition puzzle, and more questions about what else is hiding in there. 10th, amateur astronomers are seeing some weird stuff. In high-quality images, you don't just see the main antitail. There are faint, almost parallel lines, maybe from separate outgassing events or particle streams. Professionals haven't confirmed these yet, but when multiple independent observers catch the same thing, you have to take it seriously. 11th, there's a gap in the observations. Around perihelion, the comet got too close to the sun in the sky, making it impossible for most ground-based telescopes to keep watching. Some space telescopes and spacecraft got snippets, but not the whole show. So there's a window where anything could have happened. An outburst, a big change in the antitail, who knows? We just don't have the data. 12th, the antitail seems to be shifting. Several observers have noticed its angle changing, not wildly but enough to measure. And it doesn't line up perfectly with expected changes in how we're viewing the comet. If that's real, it means the structure is alive, maybe reacting to a spinning nucleus or changing activity. 13th, where's the dust tail? Usually, that's the most obvious part of a comet, a bright streamer trailing away from the sun. With 3I Atlas, you see some faint dust emission, but it's nothing compared to the antitail. The sunward structure is the star here, which is the opposite of what you'd expect. It's just one more oddity in a comet that keeps surprising us. 14th on the list, the comet's brightness. 3I Atlas has been shining a bit more than people expected, given its size and distance. Nothing wildly out of line, but it's noticeably brighter than models predicted. That could mean the nucleus is actually bigger than we thought, or maybe it's just reflecting more light. Or there's something going on with the coma or the debris around it. Maybe it's scattering sunlight in ways we haven't accounted for. And then there's number 15, the one that keeps coming up lately, the antitails collimation. 500,000 kilometers of dust and gas, all squeezed into a narrow beam just 6 to 8 degrees wide, shooting out from the night side of the nucleus. That's the odd part. Those regions are in shadow, shielded from the sun, yet they're still active. Something down there is keeping it warm enough for ice to sublimate, even in the dark. Sure, natural comets can pull off tricks like this now and then. Sunlight absorbed during the day can work its way deeper, heating the subsurface and fueling jets from shaded spots. But keeping that up for weeks or months and producing such a tight, organized jet, that's pushing the limits of current models. So that's it. 15 weird things. Each one by itself maybe you can explain away. Make enough assumptions and each quirk finds a home in the realm of possible. But stack them all together and you start to see an object that doesn't quite fit what we know. It's an interstellar comet, sure, but either it's different from anything we've seen in the solar system, or we're missing something big in how we understand these things. Of course, not everyone sees it that way. The counterarguments matter. Some astronomers don't think these features are all that strange. Jason Wright at Penn State, for example, has looked at 3I Atlas and isn't convinced there's anything extraordinary going on. He's pointed out that antitails aren't unheard of. Comet Kohoutek had one, and second in his geometric model explained it pretty well. Other comets have shown similar features, too, given the right circumstances. Just because 3I Atlas's antitail has stuck around longer doesn't mean it's some new kind of phenomenon. Maybe it just happens to line up with Earth's viewpoint for longer as we orbit the Sun. Wright also points out that the physics in the Loeb and Kido model is totally standard. Sublimating ices, uneven emission, radiation pressure sorting out the dust grains, nothing exotic there. It's just regular comet science applied to a weird case. The fact that their model actually matches what's been observed, the brightness, the shape of the antitail, suggests that a natural explanation covers it. And there's another thing. Wright warns against piling up anomalies as if they're all separate proof that something's off. A lot of these listed features are connected. For example, if you explain the axis alignment, you probably deal with the jet collimation too. As for the orbit lining up with the ecliptic, it's rare but not so rare that it's shocking, especially when we've only seen a handful of interstellar objects so far. Our sample size is tiny. Drawing big conclusions from just a few cases, that's jumping the gun. On the idea that the antitail somehow breaks physics, Wright disagrees completely. Sure, it challenges what we expected at first. It means we need better, more detailed models than the quick and dirty ones. But the underlying physics, radiation pressure, jets from sublimation, orbital dynamics, we get that stuff. There's nothing here that tramples on thermodynamics or relativity. Maybe we need to rethink how dust grains behave in these kinds of comets, but honestly, that's just how science moves forward. Casey Liss, who's also been digging into 3I Atlas data, has gotten pretty frustrated with all the talk about NASA or other agencies, supposedly covering things up or downplaying the weirdness. Liss says science is working exactly like it should. People see something unusual, they report it. Others build models, debate ideas, write papers, argue at conferences. There's no cover-up. There's just the usual back and forth that happens when the data's tricky and nobody's sure what the answer is yet. Liss points out that some of these size estimates people are tossing around, especially the claim that Hubble shows the nucleus is way bigger than we thought, just don't hold up. The Hubble telescope picks up the combined brightness of the coma and the nucleus, but to separate them, you have to make guesses about how much light comes from dust scattering versus what bounces off the solid surface. If you get those guesses wrong, your size estimate changes. In his own paper, Liss gives a reference size for comparison, not some final answer, and he's been pretty upfront about that in every conversation since. So, where does that leave us? We've got an object that's definitely odd but not impossible to figure out. The data is fascinating, just not quite enough yet to lock things down. The models seem to work, but only if you set them up just right. And the debates, well, they're lively, and that's a good thing. The community isn't arguing over whether 3I Atlas is interesting. That part's settled. The real question is how interesting it is and what we should make of it. But there's more going on here than just the details of one discovery. There's this bigger shift in astronomy that's been picking up steam over the past few years, and 3I Atlas lands right in the thick of it. We're in a new era now. Interstellar objects aren't just wild ideas anymore. They're real. We can spot them. We can study them. And each one that shows up teaches us something we just couldn't have learned any other way. Before 2017, everyone knew interstellar objects must exist. The logic was simple. Planets form around stars, and while that's happening, gravity throws material outwards. Some of it escapes completely, turns into an interstellar wanderer, and drifts through the galaxy for ages. Our solar system tosses out this kind of debris, so it's safe to say others do too. The galaxy should be full of these lonely bits of ice and rock floating between the stars, but knowing they're out there and actually spotting one, that's a whole different story. Interstellar objects are fast, small, and dark. They barely spend any time where our telescopes can catch them. Astronomers searched for decades and found nothing. And then, out of nowhere, Oumuamua appeared in October 2017. The Pan-SDARRS telescope in Hawaii saw it first. At first, people thought it was just another asteroid, but when they calculated its orbit and saw it was hyperbolic, moving too fast to be bound to the sun, it was clear. It came from outside. It was already on its way out, and we barely had time to snap a few pictures and measurements before it was gone. Oumuamua was weird. It might have been shaped like a cigar or maybe a pancake, depending on how you looked at the limited data. No coma, no tail, nothing to suggest it was outgassing, yet it sped up a tiny bit, like something was giving it a push. Scientists floated all kinds of natural explanations: hydrogen icebergs, nitrogen ice from some frozen world, or faint outgassing we just couldn't see. Nothing fit perfectly. Avi Loeb even suggested it might be artificial, a broken light sail or probe from another civilization. Most scientists didn't buy it, but the idea caught the public's imagination and forced everyone to think seriously about how we'd spot an artificial object if we ever ran into one. Then, 2 years later, in August 2019, 2I/Borisov showed up. This one looked way more like a normal comet. It had a coma, it was clearly outgassing, and we could measure its makeup: water, carbon monoxide, carbon dioxide, the usual suspects. It wasn't bizarre like Oumuamua. In some ways, that was a relief. Maybe most interstellar visitors are just icy leftovers from forming planetary systems. Oumuamua was the oddball, not the rule. And then came 3I Atlas, the third one. But it doesn't quite match either pattern. It's not as outrageously strange as Oumuamua, but it's not as comfortably familiar as Borisov either. It sits somewhere in between. Or maybe it's something entirely new, with that odd anti-tail and a handful of other weird features that just don't line up with anything we've seen before. Here's the reality. Those three interstellar objects, Oumuamua, 2I/Borisov, and 3I Atlas, aren't the whole story. They're just the ones we happen to spot. The galaxy is teeming with these wanderers. Seriously, there are probably trillions drifting through the Milky Way. Every year, a handful sneak through our solar system, but most slip by unnoticed. They're too faint, too tiny, or just passing through parts of the sky we're not watching. The ones we've found. They're the lucky breaks, the bright, the nearby, the ones that just happen to cross our path. They're giving us a peek at what's out there, but we're nowhere near seeing the full picture. That's what makes this so exciting. We're right at the beginning of a brand new field, interstellar object studies. 10 years ago, nobody seriously studied this stuff. Now, the field's exploding. Our tools keep getting sharper. Take the Vera C. Rubin Observatory. It started up in 2024, and now it's pumping out more data than anyone ever dreamed of. It can catch faint, fast-moving objects earlier telescopes missed. On top of that, artificial intelligence and machine learning are jumping in, scanning through the flood of data, picking out possible interstellar visitors, and flagging them for astronomers to check out within hours. What does that mean? We're about to find a lot more of these interstellar travelers. Not just a handful, dozens, maybe even hundreds over the next decade. Each one adds a new data point. Each one helps us figure out what's common and what's rare out there. And every object carries a little bit of its home system along, a sample of what that star system was made of, a glimpse at how planets form in other corners of the galaxy, maybe under conditions nothing like our own. Take 3I Atlas, for example. It's already taught us something new. In the system where it formed, carbon dioxide ice was apparently more common than water ice, at least in the part of the disk where this comet was born. That says a lot about that system's early days, about how far out from the star you'd find different ices, about the chemistry in the planet-forming zone. We can compare that to our solar system, where water ice reigns in the outer regions. Piece by piece, we're building up a catalog of how different star systems stash their ices and gases. But then there's the big question, the one Avi Loeb keeps throwing out there, the one that Jason Wright and others keep arguing against, but that never really goes away. If the galaxy is full of debris from dead planets, and if some of those planets ever grew civilizations with technology, then shouldn't there also be artificial stuff out there? Maybe probes, maybe old spacecraft, maybe just the leftovers from ancient cosmic engineering. Just look at what we've done. Humans have barely dipped a toe in spaceflight, and already we've sent 5 probes outside the solar system. Pioneer 10 and 11, Voyager 1 and 2, New Horizons. They're all out there, drifting in interstellar space, loaded with information about Earth, and they'll keep going for millions or billions of years unless something smacks into them. If we can manage this with chemical rockets and 1970s tech, imagine what a truly advanced civilization could pull off. They could launch thousands of probes, millions, maybe even build machines that copy themselves, spreading through the galaxy over millions of years. Or maybe they'd send out simpler, tougher instruments, long-lived, drifting between stars, just waiting to beam home a message when they pass the right spot or reach a new system. If a probe from somewhere else flew into our solar system, how would we even spot it? That's the tricky part. If it's dead, just drifting, no lights, nothing, it would look like any other rock out there, maybe an asteroid or a comet. If it's barely alive, just keeping itself pointed in the right direction and sipping power from the sun, it might drift a bit off course in ways we'd usually blame on outgassing. You'd have to really dig into the data to notice anything odd. But say it's doing something on purpose, something a natural object just doesn't do. Maybe then we'd see weird structures or behaviors that don't fit our usual models. But honestly, unless we send a spacecraft to check it out up close, proving it's artificial from a distance is nearly impossible. This is the heart of the whole debate about 3I Atlas, and it gets philosophical fast. Nobody is flat out saying it's artificial, not Avi Loeb, not anyone in mainstream science. The evidence just isn't there. We're not picking up any radio signals, nothing that screams technology, no materials that couldn't show up naturally. But there's this quiet question running underneath it all, in papers, on blogs, in conference hallways. If we ever did run into an artificial object from another star, would we even know? Could we really tell it apart from a weird comet? Or would we just keep finding ways to explain away anything strange? Because that's what scientists do, fit things into natural explanations, demand extraordinary evidence, and set the bar for artificial so high that nothing short of a flying saucer would count. The antitale isn't the smoking gun. It's weird, sure. It doesn't fit the simplest models, but it's not impossible to explain. Loeb and Kido's ice grain idea holds up. They use regular physics. It matches the observations. Sure, it needs a few things to line up just right. A certain spin, a specific way for the dust to shoot out, but nature pulls off special conditions all the time. Look, the solar system itself comes from a chain of ridiculous coincidences. Even total solar eclipses are just a lucky match of sizes and distances, but we don't need aliens to explain them. So the antitail, by itself, isn't proof of anything beyond a strange interstellar comet doing its thing. What it does is make us pay closer attention. It pushes us to get more data, sharpen our models, and keep an eye on 3I Atlas as it heads out. Because if new weirdness pops up, something we just can't explain away with natural processes, then maybe the artificiality question gets real scientific traction. We're not there right now. We might never get there with this object, but we're watching and we're not letting it out of our sight. Since 3I Atlas swung past Earth on December 19, telescopes everywhere have been on high alert. Observatories across the US and around the globe are tracking it, snapping photos, grabbing spectra as it fades into the distance, away from the sun and farther from Earth. We want to see what happens to that antitail. Does it stick around as the comet cools off? Does it just fade, or does it start to break up? Does it vanish completely, and if so, how far out does that happen? That's what we're trying to find out. Hubble on the schedule for more comet observations in early 2026, as long as the comet stays bright enough. There's a chance the James Webb Space Telescope might get involved too. But honestly, JWST time is like gold. Every minute is fought over, and getting approval for another look at a comet means convincing people it's more important than 100 other projects. Still, people are interested. Enough astronomers think 3I Atlas is worth it, which says a lot about how seriously everyone's taking these weird features, even the researchers who usually lean toward natural explanations. Amateurs are still a huge part of the story. When the comet gets too faint for the big observatories, or when professional telescopes move on to new targets, these dedicated backyard astronomers keep watching. They're posting photos everywhere: forums, social media, preprints. They're sharing and comparing data, working together. And honestly, sometimes they're spotting details the pros miss, partly because the big telescopes are looking for something else, or their instruments just aren't set up for the same kind of observations. This is one of the best parts of modern astronomy. Anyone with some know-how and a decent setup can make a real difference. They can find something new. They can even challenge what the professionals think. Take Paul Craig's, for example. His sharp photo of 3I Atlas back in November got everyone talking. People argued about whether the structure he caught was real or just a quirk of image processing. The debates got heated, but the point is, it made people look closer. It forced questions about what we're actually seeing. That's the real value here. Not in winning one theory over another, but in staying alert. In not settling for easy answers when the evidence is still murky. Pushing for more data, tougher tests, and being ready to admit we might be missing something big. Look at the history of astronomy. It's packed with moments where we had to admit we were wrong. Earth at the center. Nope, it's the sun. Universe static. Turns out it's expanding. Black holes at the heart of galaxies, planets everywhere. Every one of these ideas sounded wild at first. People resisted them, then the evidence piled up and changed everything. We're not at that tipping point with 3I Atlas. Not yet, but we're definitely rethinking what interstellar objects can look like, how they behave, what they're made of. This comet, with its weird antitail and all these surprises, is speeding up that process. So what's next? What can actually help settle some of these debates? First off, we need better limits on the comet's size and shape. If we could just get a good look at the nucleus, see its real shape, clock its spin, figure out if it's a solid chunk or a loose pile of debris, that would clear up a lot. We'd know how much mass it's got, how it reacts to jets of gas, maybe even spot different regions on the surface that explain those jets. We could predict which parts get sunlight and which stay in shadow as it turns. Hubble can't pull this off. The nucleus is way too small and distant, even at its closest. It was just a faint dot. But with a little luck, if the comet stays bright and we catch it at the right angle, future observations might finally reveal those details. Next up, spectroscopic monitoring of the antitail itself. Most of the spectra we have right now come from the coma, the fuzzy region around the nucleus. Basically, those just tell us what gases are floating around in general. But what if we could zoom in and get a spectrum of the antitail specifically, that narrow little beam? Then we could finally see what it's actually made of. Is it mostly dust? Are there ice grains in there? Maybe some gas too. And what if we spot weird molecules or ions, something nobody expected? That kind of data helps us figure out if we're looking at a geometric dust trail or something more like sublimating ice grains. It might even reveal something totally new. After that, think about high-cadence photometry. That just means measuring brightness over and over, watching for changes, rotation, flickers, outbursts. If the nucleus spins and the antitail is hooked to an active spot on its surface, the antitail's brightness should change as that patch turns in and out of sunlight. If we can track those variations and pin down a period, that would be strong evidence for the idea that a rotating jet is driving the antitail. And if the brightness doesn't budge, then maybe something else is going on, some other emission process, or a structure that doesn't care about the nucleus's rotation at all. Then there's polarimetry, measuring how light is polarized. It sounds technical, and it is, but in simple terms, dust and gas scatter light in different ways. Little grains polarize light differently than big ones, and ice gives a different signature than rock. By measuring polarization from the antitail itself, we can get a solid read on what kind of particles are making up this structure and how big they are. People have done this with parts of the coma, but doing it for the antitail would be a big step forward. Next, astrometric tracking. This is all about precisely measuring the comet's position and comparing it to what gravity alone would predict. If the comet's acceleration changes as it moves away from the sun, that tells us something about what's pushing it. Outgassing should fade as the comet cools, so if the acceleration doesn't drop or does something weird, well, that's a big clue there's more going on. Don't forget about searching for fragments. If the nucleus is fragile, maybe because of thermal stress or spinning too fast, it might just crack apart as it heads out. Fragmentation is dramatic when it happens. You suddenly see fresh material from inside, new outbursts, and now you've got multiple pieces to track. That means more data, more chances to understand what's really going on. We haven't seen big breakups yet, but that doesn't mean we won't. We should keep looking. All of this is tough. You need time on the world's busiest telescopes, clear skies, and a comet that's close and bright enough to actually see. 3I Atlas is heading out fast. By mid-2026, it might be too faint for anything but the largest telescopes. A year later, it'll probably be lost to ordinary observation, just too dim to follow. The window for real study is right now, in these last few months while it's still close. This chance won't come again. Whatever we learn, or don't learn, now will shape how we understand this object forever. And honestly, there's a human side to all this that scientists don't always talk about. We're trained to be skeptical, to demand proof, to avoid jumping to wild conclusions. That discipline is important, it keeps science honest, but it can also slow things down. When you've spent years building models and publishing papers and then an object comes along that doesn't fit, the instinct is to tweak your models, fiddle with the numbers, make it all work somehow. That's normal. That's how science usually moves bit by bit. But sometimes small tweaks aren't enough. Sometimes something is weird enough that you have to question the whole framework. Realizing you've hit that wall isn't easy. It takes guts to say, maybe we don't understand this as well as we thought. That's not a comfortable place to be. It opens you up to criticism, to pushback. It makes you vulnerable. But without that willingness, you can miss the most important discoveries. The 3I Atlas team is right in the middle of this debate. You've got people like Loeb who aren't afraid to shake things up and say, hey, maybe we're missing something here. Maybe the usual explanations don't quite cover it. Then there are the more cautious voices, Wright and Liss, for example, arguing the natural explanations hold up just fine if you look closely enough, that there's no need to get wild or question everything we know. Both sides have a point. They're all looking at the same data. It just comes down to how much you care about the weird stuff versus how much you trust the models. Honestly, that push and pull is what keeps things interesting. It's the engine that moves science forward. Each side has to make their case stronger, find better data, test their ideas harder. The real problem isn't that someone's wrong. It's that we might never get a clear answer because the comet fades away before we can collect what we need. Then we're stuck, left with an intriguing mystery that fizzles out, never really solved. That's the risk right now. Time's running out. The comet's getting dimmer and soon we'll lose our chance. If we want answers, if we want to know whether the anti-tail is just a trick of the light or something real, if the oddities are just flukes or clues to something bigger, we have to act fast. We've only got a few months left before 3I Atlas disappears for good, just a fleeting visitor we barely got to know. But there's a bigger picture, too. This isn't just about one comet. It's about how we handle these rare interstellar objects in general, how we get ready for the next one, how we squeeze as much science as we can out of these brief encounters. People are already thinking ahead, pitching the idea of spacecraft that sit ready to launch the moment we spot a new interstellar visitor, racing out to meet it and collect up-close data. The European Space Agency's Comet Interceptor, set to launch later this decade, is built for exactly that. It'll wait out in space, poised for action, ready to intercept a pristine comet or an interstellar traveler and send out probes from multiple angles. That's the dream. We're not there yet. For now, with 3I Atlas, all we can do is watch from afar. Telescopes on the ground, telescopes in orbit, catching whatever light we can from millions of kilometers away, trying to piece together a story from the faint signals that reach us. It's a little frustrating. It's indirect. But it's what we've got, and for now, it'll have to do. Even with all the things we still don't know, we've actually figured out a ton. For starters, this comet didn't come from around here, it's from another star system. It formed out there in some freezing carbon dioxide-rich place. And now it's doing something wild. It's building a structure so unusual, it might be the only one of its kind we've ever seen. Its rotation axis lines up with the Sun, which is odd. It's swung close to Mars, and soon it'll pass by Jupiter's orbit. In a lot of ways, it's throwing a wrench into our old models, making us rethink what we know about comets, about what's possible, about the stuff floating between the stars. But honestly, the list of things we don't know is just as long. We can't pin down the nucleus's exact size or shape. Is it solid, or is it a loose pile of rubble? Is it uniform all the way through, or layered like an onion? No clue. We're still scratching our heads over what's powering that anti-tail. There's no clear answer. Are all these weird features connected somehow, or are they just random quirks showing up at the same time? We can't tell. And is this comet one of many like it, or did we just get incredibly lucky or unlucky to spot such a rare outlier? Nobody knows. There's one more thing we can't say for sure. Is everything we're seeing just natural? Most scientists say yes. The observations fit what we expect from natural processes, so jumping to stranger conclusions just isn't necessary. But let's be real, consensus isn't the same as proof. It's just a well-informed guess based on what we have so far. People have been wrong before. So yeah, it's good to trust the experts, but we have to stay open to the idea that sometimes the weird stuff, the outliers, the things that don't fit, end up teaching us something new. That's exactly where 3I Atlas sits. Odds are it's totally natural, almost definitely, but almost leaves a crack open. A little room for doubt, and for questions that keep us up at night. We're staring at something we just don't fully get. Let's talk about that anti-tail again, because honestly, it's the heart of the puzzle. Picture this. It stretches out 500,000 kilometers. That's bigger than the distance from here to the moon. It's a structure larger than the whole Earth-Moon system, built from particles, grains, or maybe gas, something organized into a narrow beam that stays tight across all that space. It's aimed straight at the sun, and it's been like that for months. So if it's just a trick of geometry, dust lined up with the comet's orbital plane making an illusion, why hasn't it faded as the Earth moved around the sun? The angle between us, the comet, and the sun has shifted a lot since summer. If it was just a visual alignment, it should have changed shape, maybe even disappeared by now. But the anti-tail is still there. Or maybe instead we're seeing ice grains shooting out from the nucleus. But if that's true, the beam is incredibly focused. The opening angle is tiny, like a laser pointer instead of a flashlight. The grains would have to be coming from a really small spot, and the jet would have to go on for days or weeks, even as the comet spins and moves farther from the sun. We don't have a good explanation for how that could happen. Comet jets usually spray wide, not sharp. They blur out fast. This one doesn't. Then again, maybe it's not dust or ice at all. Maybe it's a plasma structure, some kind of ionized gas shaped and held in place by magnetic fields. Comets interact with the solar wind, and that can make long, skinny plasma tails. But those usually point away from the sun, not toward it. For this to work, you'd need a weird magnetic setup, something we almost never see. Could it happen? Maybe. Do we have real evidence for it? Not really. The spectra don't show the strong ion lines we'd expect if this were plasma. But we can't rule it out completely. With better data, we might find something we've missed. Or maybe that antitail is just leftover debris. Picture this. Early on, before anyone started really watching, the comet might have had some kind of outburst or broke apart a bit. Chunks of material shot out, and some of it ended up on a path that, from where we're looking, seems to point right back toward the sun. Now it's just drifting, no new stuff being added, fatting out as it goes. We're basically catching the final act of something that already happened. That would explain why it sticks around. Nobody maintaining it. It's just hanging there like a fossil from some earlier drama, but there's a snag with that idea. If the material was really just coasting, it should be spreading out. Each bit travels a little differently, and over time that should mess up the shape, make it blurrier, wider, less crisp. But if you look at the images, you don't see much of that. The antitail still looks sharp. Honestly, every explanation seems to have its own set of problems. Every model pushes the boundaries of what feels reasonable. That's usually a sign you're dealing with something truly odd. Not magic, not impossible, just stubbornly hard to explain. The kind of thing that forces you to dig deeper, double-check yourself, push at your own assumptions. You can see this tension in the papers and blog posts about 3I Atlas. The authors don't have it all sorted out. Loeb's work, for example, it's packed with equations and detailed models of how these particles move, how sunlight pushes on them, how fast the ice turns to gas. It's all very thorough, no hand-waving. The models show you can match what we see, but only if you set the dials just right. They admit it, you need things to line up in a very specific way, and it's not obvious those conditions actually happen out in space. So are these scenarios likely? Or is it all so precise that it hints at something else going on? Wright's critiques go deep too. He's not saying the observations are wrong. He's saying, look, if you want to claim something is truly weird, outside the reach of known physics, you need rock-solid proof. He's right, that's how science should work. Big claims need big evidence. But here's the catch. If you set the bar too high, demand certainty before you'll even talk about alternatives, you can end up ignoring something important. You risk explaining away the real surprises just because you're clinging to what's familiar. Finding that balance is tough. There's no recipe for it. It's a judgment call, depends on experience, on how much you trust the data versus the models, on where your instincts land. Researchers can disagree, and that's fine. That's how it's supposed to go. This kind of debate, out in the open, is actually good for science. People get to see how it really works, not some neat, step-by-step march toward truth, but a messy, noisy back-and-forth where smart folks can look at the same thing and see it in completely different ways. One thing's for sure, 3I Atlas has grabbed attention like almost no other comet. It's been all over science news, discussed at conferences, spawning papers, lighting up arguments online. Everyone from backyard stargazers to seasoned pros is talking about it. That kind of buzz doesn't happen unless something genuinely weird is going on. And what's really fascinating isn't just one odd feature. It's the whole pattern. Every new observation just adds to the mystery, never quite clearing things up. Some objects are like that. They're Rorschach tests. You see in them what you're ready to see. If you think comets are straightforward and their physics is basically sorted, then 3I Atlas just looks like a tricky but natural case. A comet that needs some fancy modeling, but nothing game-changing. If you're open to the idea that maybe we've gotten a little too comfortable, maybe we don't actually know everything comets can do, then 3I Atlas feels like a wake-up call. Maybe it's showing us gaps in the models, stuff we haven't really seen before. And if you're willing to let your mind wander further, if you think, what if this is an artificial object? Is a question worth asking, even if it sounds far-fetched. Then 3I Atlas becomes even more interesting. It doesn't prove anything about alien tech, but it doesn't rule it out either. It just sits there, weird and unexplained, daring us to pay closer attention and keep an open mind. Right now, you've got three different camps arguing it out, each with their own take. That's not going to change anytime soon, not as long as new data keeps showing up. The big question is, will we ever have enough? Will the evidence get sharp enough to settle the argument? Or will 3I Atlas just drift off like so many comets before it, leaving us with more guesses than real answers? As of late December 2025, the comet's still out there, still active with that weird anti-tail. People on the ground are pointing their scopes at it. Space telescopes are chasing it too. Data's pouring in. Papers are flying out. Models get tweaked. New theories pop up, and science does what it always does, turns confusion into more questions. We're learning, sure, but half the time what we're learning is just how little we really know. Fast forward a few months. 3I Atlas will slip away, too faint for anything but the biggest telescopes, and even those will be pushing it. It'll cross Mars's path, then Jupiter's, then keep going, out past the edges of the solar system and back into the dark between the stars. It swung by our corner of the galaxy for a handful of years. We got a few months to stare at it. Then it's gone, off on a million-year journey. Maybe, if it ever shows up near another star, some other astronomers will spot it and puzzle over it just like we did. But right now, while we still have time, the main question hangs in the air. What exactly are we looking at? Is this a comet that formed in some wild carbon dioxide-rich environment? Did that create a nucleus with just the right spin and let it shoot out those narrow jets we've seen? Does that explain everything, or are we missing something? Some hidden process, some bit of physics, some crucial detail that would finally make all the pieces fit. Here's the one thing nobody can ignore. The anti-tail points straight at the sun. That's the fact at the center of it all. Every model, every debate, every wild theory starts there. Comet tails don't do that, except this one does. And until someone can spell out exactly why clear enough for the doubters and the dreamers, 3I Atlas stays a mystery. Maybe the biggest one in astronomy right now. A visitor from another star. A comet breaking all the rules. A structure that shouldn't exist, but there it is. 500,000 kilometers of organized dust and ice pointing back at the sun, the very thing that should be blowing it away. We're watching, we're measuring, we're chasing answers, and the clock's running out. Soon it'll be too late. 3I Atlas will vanish into the dark, and all we'll have left is the data we managed to grab and the questions we couldn't quite nail down. This is it. The moment. Final observations, last shots, the window closing on an interstellar visitor that showed up out of nowhere and left us with something we've never seen before. Something that shakes us up, makes us wonder, reminds us just how much is still out there, waiting, beyond our tiny slice of the universe. The anti-tail points at the sun, and we're still trying to figure out why.